Welcome to session number 1 of the Fundamentals of IPOS. We're going to be looking at IPOS's features, and we're also going to look at how to set up the system to write an IPOS program. So this is moving past the introduction and getting us into some of the meat of IPOS. So let's go ahead and get started. First of all, I'd like to talk about some of IPOS's features and capabilities. This is just a quick summary, but these are some of the things you'll be dealing with as you work through the different sessions. First of all, IPOS is particularly suited for positioning applications. Now, that doesn't mean you can't use it for speed control or torque control. You can. But positioning is its specialty, and that's what most people use it for when they're writing a custom IPOS application. IPOS makes full use of encoders for maximum precision. In fact, you have to have an encoder on your motor if you're using IPOS, because IPOS needs that precision. But it's going to take advantage of that and give you really super control if you have a decent encoder. IPOS gives complete access to the input-output system, the I/O system, and that includes any option cards that you have installed in the VFD that maybe expands the I/O beyond the built-in capabilities. IPOS works with both analog and digital information. If you have analog inputs and outputs, you can work with those. If you have digital inputs and outputs, you can work with those. So it's very flexible. It's also got a lot of communication flexibility. It can communicate over the RS-485 port built into the VFD. It can use the S-Bus, that's SEW's system bus, which is based on the CAN protocol. And also it can communicate over any field bus cards you have installed in the VFD. It accommodates multiple ramp types, so you can accelerate and decelerate in a variety of ways. It supports 9 different referencing modes, so there are many ways to get your drive referenced. You can control by speed, position, or torque. We'll be exploring speed and position in this class. We will not be exploring torque because that's kind of hard to simulate in a classroom environment, but we will be looking at position and speed. You have something called multitasking code execution with interrupts. Now, if you know what that is, great, but if not, I'm just about to explain it, so don't worry about it. It's really a nifty little feature. There's also something called error handling and watchdogging. If you have a problem when the VFD is running, you don't necessarily want it just to die. Maybe you want it to stop in some controlled way and handle the error in a very specific manner. That's possible. Watchdogging allows the VFD to automatically restart itself if it should crash for some reason. That's another handy feature because sometimes you don't want to have to send someone to a dead VFD to make them just manually restart it. So again, that is possible. And just a reminder, we develop all our programs and debug them through MOVITools Motion Studio, the free SEW software that is also used for working with the drive. So presumably you're already familiar with it in that capacity, and we'll just be taking it a notch further as we get into IPOS programming. Now, let's talk about IPOS's memory. IPOS has access to 2 different kinds of memories built into the VFD. And this may seem a little unusual to you because on a PC we basically only have one and everything lives in there, but in a VFD, such as the MOVIDRIVE B, we handle it a little differently. There is a 16 kilobyte program memory. That's where your IPOS program lives. And you may think, boy, 16 kilobytes, that's minuscule. My PC has tons of gigabytes in it. Well, this isn't a PC. It's a VFD doing a very specific task. 16 kilobytes is actually quite a bit, and you can write a very large IPOS program that does some very clever things in that. So don't be put off by that, even though it seems really strange today. All right, so there's the program memory, and then there's also what's called the data memory, and it's got 1,024 words. Notice it's not bytes or kilobytes or anything, it's words. I'll explain what that means in just a second. Again, that seems like a very small amount of memory, but actually it's plenty. You will probably never exhaust it. Now, program memory isn't accessible. Now, what I mean by that is that the program can't read its own memory. Of course, you can access it when you install the program into the VFD through MoviTools Motion Studio, but it's not readable by the program itself, and you don't need to, so it's not a handicap. Just be aware of that. The data memory is what you can read and write. We call these variables because they're places you can store information that varies, that changes as the program runs. And we'll be using variables heavily in this course. They're very important. Now, I said they're words, not bytes or kilobytes or anything. And that means they are 32 bits long. All right, so these are 32-bit long variables. There are 1,024 of them. And that allows you to store some pretty big numbers. 128 of these words are non-volatile. That means that they're stored in flash memory. So when you turn the VFD off, they don't evaporate. That means you can preserve 128 variables between power cycles. The remaining 896 are volatile, so when you turn the power off, they just go away, become zero again. So if you need to preserve something between power cycles, you store it in one of those 128 words of non-volatile memory. 108 of the total words are used by the system. The system uses this for its own use and also for reporting status information and other things. And you can access many of the system's reserved words as well. So you have a total of 916 available to your program for general purpose use, the 128 non-volatile ones and the 788 remaining ones. We label them H0 through H1023. In fact, they're often just called the H variables because they all begin with the letter H. And that's one way that you can access them, by the name H and the number after them. There are other ways. We'll get into those as we go along. And here's the memory map of data memory. You notice H0 through H127. That's the non-volatile variables. That's the variables that don't evaporate when the power goes off. H128 through H452 are just general purpose user variables. You can use those for whatever you like. H453 through H560, those are the system variables and the reserve variables that the system keeps for itself. And then finally, H561 through H1023, again, are just general purpose variables available to you. Now, just a reminder, this is the memory map of a MOVIDRIVE B, which is what we're using, but the memory sizes are different for other products like the MOVITrack B and the field bus distributors and other things. We're not getting into that in this class. We're not working with those products. But if you are, you'll need to look up how the memory differs by going into the IPOS manual. Now let's talk about the numbers that we shove into those variables, into those memory locations. 32 bits gives you a fairly big number. All variables and numbers are 32 bits wide, and they are signed. That means they're positive and negative. All right, an unsigned number isn't really either. It's just a magnitude, but these are signed numbers. They're plus or minus. This is different from the C programming language where you can have both signed and unsigned. Most other languages also allow that, but IPOS does not. IPOS numbers are always treated as signed. And the decimal range is roughly plus or minus 2 billion. So you can store a pretty big number in there. That's the decimal range. So here is the decimal range graphically. You can see zeros in the middle. You have the negative numbers on the left, the positive on the right. If we express this in hexadecimal, which is what we often use in controller applications, then here's the range. And if this looks a little weird to you, don't worry. I'm going to explain in a later session how signed numbers are encoded in binary and hexadecimal. It's a little weird. If you've never done it before, it seems very strange. If you're an experienced programmer, you probably already know. But this is the hexadecimal equivalent of the decimal range. Now, here's another little bit of weirdness with binary numbers. Numbers wrap around if you exceed their limits. In other words, let me show you an example. Let's say you're up there at the positive 2 billion end, and you add 1. What happens? Well, obviously, it's now too big, to fit in 32 bits, so it just rolls around and it becomes the biggest negative number. Yes, that's weird, but that's the way it works. In fact, all computers do this, and you just have to have the intelligence in your program that if your number is getting a little too big to accommodate that, so it doesn't wrap around and give you a crazy number that makes no sense. The same thing happens at the other end. If you start at the negative 2 billion end and you subtract 1, it rolls around and becomes the biggest positive value, positive 2 billion and some numbers. Okay, so do be aware of that. If you think your numbers are kind of getting near the edges, then your code needs to be able to accommodate that. Now let's talk about the system variables. These are variables the system reserves for its own use. They are documented in the manual. Here's an example of one. They're the variables H453 to H560. And they do all kinds of things. They contain information about the system, its status, its hardware. Some are just used for IPOS's internal use, and it doesn't tell you what it's doing with that variable. It just says you can't use it. And here's another interesting little fact. Some are read-only. In other words, you can't change them. You can only read them to see what they're saying. Some are write-only, meaning you can write into them, but you can't read them back. And some are read-write. You can do both. The manual will explain this, so as you read about these variables, you'll be able to decide how they work. And as I said, some are unspecified, but the system reserves them for private use, so just don't mess with those. You can access them by their H number. In other words, in your program, you can say, for example, I want to read H473, and it will accept that. But you can also give them a dedicated name. So take a look at this example here, H473, that's the H number, but there's also an equivalent name called status word. And it's often nicer to use the name because the name usually tells you what it does. You don't have to remember H473 does this. You just remember, okay, I'm using status word because that's giving me the status of the VFD. These are discussed in detail on pages 29 through 39 in the manual, so go there to learn about these. I'll be introducing some of these in this class, but some I leave up to you to explore. Here's an extremely useful one, though. Status word H473. It provides a complete picture of the VFD's current condition. And you notice it's got individual bits in there that are changing to tell you different things. Like it's telling you if the brakes applied or released, if the motor's moving, the magnetic field is rotating, if the drive is referenced. There are just all kinds of handy little bits in there to tell you what's going on. We will be using this variable a lot in programs because you need to know what's going on inside the VFD. Now, what about the I/O system, the input-output system? As you know, MOVIDRIVE B has built-in I/Os, but you can also expand those by putting cards in there, like the DIO11B, which gives you some extra inputs and outputs. And there's also an encoder card that has an SSI encoder on it and also has some extra I/O. How's I/O handled? Well, we have both binary and analog input and outputs, so of course they require slightly different handling because analog inputs and outputs give you a range of numbers, whereas binary is just an on or off. And some of these can be accessed through the system variables. There are dedicated system variables to access different parts of the I/O. And some require special commands that access them. So for example, H520, which is called INP level B, reads all the inputs, both the built-in ones and the option ones on any installed cards. So you can read all the binary inputs and just see what their state is. There's H521 out P level B. It reports the status of all the outputs, both the built-in and the ones on the option cards. It tells you what their current state is. Are they on or off? H481, standard out P IPOS, allows you to control the standard outputs. Those are the ones built into the VFD. H480, opt out P IPOS, controls the ones on any option cards. So those are in separate variables. There's H479, ANA out P IPOS. It allows you to control the analog output option. And H478 does the same thing on the second analog output option. To access the inputs, you don't use the system variables. There are commands to read the analog inputs, and you will eventually be writing a program that reads those. So that's the I/O system, how it's handled. Now, I've alluded several times to multitasking. It's now time to explain what it is and why we care about it. Multitasking makes the programmer's life a lot easier because it breaks the program into separate sections that operate independently and simultaneously. What do I mean by that? Basically means the VFD can run several independent programs that coexist and just run. Now you may wonder, why on earth would you want to have several programs running at a time? Well, it allows you to break up your program into logical sections and just let them run independently of each other. Now, why you would do this, this guarantees that critical tasks are happening reliably and in a predictable amount of time. That's called deterministic, meaning you can determine how often it gets attention. But then maybe non-critical tasks that don't have to be done in a particular time can just use whatever time is left. Let me give you an example of this. Motion control is something you'd probably want to be deterministic. You want your motion control to be happening precisely. So you give it its own dedicated task, and that task says, I'm going to do this at very precise time intervals. So motion control is highly predictable. But then maybe you have communication where you're talking to other VFDs. That doesn't have to necessarily happen down to the millisecond. It can happen when it happens. And so you put that in a different task and let that run. And maybe then user interface, controlling the lights, reading the switches, whatever other kind of user interface is attached. That's probably something that's pretty low priority because it doesn't matter if a few milliseconds extra go by or not. So maybe that's your lowest priority. By separating these functions into separate tasks, it makes it easier for you as a programmer. All right, enough said about that. We'll look at multitasking actually quite a ways down the road. Now, the MOVIDRIVE B under IPOS has 3 separate tasks or 3 independent programs that can run, and we just call them task 1, 2, and 3. So not very imaginative, but there you are. Now, task 1 is mandatory. That's the main program. This is always going to run, and it's started by MOVITools. You'll start it up in MOVITools to run, and then it just sits there in the VFD and does its thing. Tasks 2 and 3 are optional. You do not have to use them if they're not relevant to the program you're writing, but you start them or stop them in the program itself. So these are kind of like your secondary tasks. Tasks 1 and 2 are deterministic. They have a guaranteed execution time. Task 3 uses whatever time is left, so that depends on how you've configured tasks 1 and 2. Now, we rate performance of the tasks in what's called assembly language instructions per millisecond. If you're writing in assembly language, then the VFD is going to execute a certain number of those instructions every millisecond. Now remember, we're in compiler language, and one line of compiler code turns into multiple assembly language instructions. So this metric isn't terribly useful in compiler. It just gives you an idea of how the tasks are working. So task management definitely requires a little skill in just trying to estimate how to set them up. Here's how you do it. Task 1, you go into the parameter tree of the MOVIDRIVE B, go to parameter 938, and you can set it there. It defaults to 1 instruction per millisecond, but you can set it as much as 10. Task 2 is controlled by parameter 939 in the parameter tree. It defaults to 2 instructions per millisecond, so it actually runs a little faster, and you can set it up to 11 maximum. Now, here's a rule. Task 1 plus task 2 must always be less than or equal to 12 instructions per millisecond. If you set it to anything else, you can get some weirdness. So be sure that they never add up to anything greater than 12. Now, task 3 guarantees at least 1 instruction per millisecond, but it just uses what's left over. So it's more common that it's giving you about 20 to 40. So it can be faster, but it's not guaranteed. All right, that's the general picture. And you can also interrupt tasks. Now, you may wonder, what does interrupting mean? Well, let's look at that. I'll give you a really good example of what an interrupt is. An interrupt is an event that halts normal program execution and diverts to an interrupt service routine. Okay, that's clear as mud. What does that mean? Let me give you an analogy to make this all make sense. Let's say you're sitting at your desk checking your email. That's your normal daily activity. That's your main task that's running. Now, you're going along doing this, and all of a sudden, the phone rings. The phone is an interrupt. It says, stop what you're doing and pay attention to me. And that's exactly what you do. You stop checking your email. You pick up the phone. You say, hello, who is this? How can I help you? You talk on the phone. And then when you're all done with your phone conversation, you hang up. And guess what you do? You go back to checking your email. All right, that's what an interrupt service routine is. It's a little piece of code that when the interrupt happens, it just pauses what the main program was doing, runs off, runs the interrupt code, and then when it's done, it goes back to where it was when it got interrupted. So really simple, actually. And the reason we do interrupts is because it allows us to handle things that need to be serviced right now, not later. That's what they're for critical tasks that need attention instantly. Now, what happens if you get another interrupt while you're in an interrupt? That's sort of like if your boss walks up to you while you're on the phone and says, I've got to talk to you this instant. That's a higher priority interrupt. And so you tell the person on the phone, hey, can I call you back? And what you do then is you listen to your boss, then you call the person back on the phone, and then finally you go back to checking your email. That's kind of the big picture of interrupts. So interrupts can have priorities so they know which one gets top attention. You can also shut them off. That's kind of like closing your door, putting a do not disturb sign up, muting your phone, and then just ignoring it. So you can shut off interrupts too. So if something can't afford to be interrupted, you can turn them off. All right, task 1 can be interrupted by these things: an error or a fault on the VFD, a touch probe connected to digital input 2 that gets touched, or there's a timer in the MOVIDRIVE, and if the timer overflows, in other words, it runs to maximum and wraps around, that can trigger an interrupt. So it's basically a timed interrupt. Tasks 2 and 3 can be monitored by a variable, an H variable, that changes to some specific value or in some specific way. You set this up. It's called monitoring a variable, and there are 4 of these available. We're not going to do a lot with interrupts in this class. That's a very advanced topic. So primarily you'll have to read the manual if you want to know about these, or at some point in the future we may offer a little advanced mini class in using interrupts. But I do want you to know what they are, so when you read about them in the manual, they'll make sense. All right, time for a hands-on task. We're going to get our MOVIDRIVE B configured and ready to go to write IPOS programs, and I'm going to give you a chance to do this, but watch me kind of step through it first in outline form, then you can pause the video, go ahead and do it, and you can unpause it and watch me do it and see if you did it right. So here's how you prepare a MOVIDRIVE B for running IPOS. Generally, you want to begin with a clean slate, so you return it to delivery state, and you do this by going to parameter 802 and setting it to yes. And just remember, you don't get a second chance with this. It will clear that VFD the instant you change it. So remember, if this is an in-service unit, you better do a backup first, or you could lose important settings or other programs that are already in there. Next, do a motor startup. Get your motor configured and started up. I'm not going to tell you how to do this because you should have taken the MOVIDRIVE B intermediate class that explains how to do it. So you will need to do that, and it will need to be appropriate for the motor you have. Now, little reminder, you must be in a vector-controlled mode. And that means VFC or CFC mode. So you set this to vector-controlled /servo. This will work either with an asynchronous motor or a servo motor, asynchronous motor. So you need to do that. You also need to be sure you've selected positioning with IPOS. All right. So even if you're going to be controlling it in speed control mode under your IPOS program, you still have to have it in this mode, positioning. Then you pick between VFC or CFC. Either one works. With an asynchronous motor, you can use either one. With a synchronous motor, a servo motor, then CFC is your only choice. So pick whatever is appropriate for your motor and what you wish to do. In general, I like CFC mode because it's the best and most precise control mode we offer. Then do all the other motor startup tasks as usual, and if necessary, tune the motor. And again, I'm not going through this because it's covered in the MOVIDRIVE B intermediate class. Finally, you need to confirm that IPOS is part of the control mode settings. And you do this by going to parameter 700 in the parameter tree and make sure the word IPOS is somewhere in there. This is a VFC mode with IPOS. You could have CFC with IPOS. Doesn't matter. They're both great. Make sure you've set the maximum speed of your motor. In this case, it's an asynchronous motor set to 1800 RPM, but set it to whatever matches your motor. Set the travel speeds, which are right here, and you should set these about 10% slower than the maximum so you have some headroom. Otherwise, you can get faults and lag errors and things like that. So your travel speed should be a little slower. About 10% is fine. So I use 1500 here. And then set the lag error to whatever's appropriate for your application. I set it to 5,000 increments. You may have to set it to more or less. Remember, lag errors generate usually faults if the encoder is too far off from what it's actually supposed to be. So if the motor isn't really matching what you've specified by more than the lag error, it will generally shut off the VFD. Now you can control what it does. Usually you set it to an emergency stop with a VFD fault. But again, this is application driven. So for this class, set it to this, that's fine. Then configure your binary inputs. Your standard ones, those are the built-in ones in the VFD. Set them to what's appropriate for the application. So probably you're going to assign a few to limit switches, maybe a referencing sensor of some sort. So set those, and any that you don't, change to IPOS input. IPOS will not be able to read them if you don't set them to IPOS input. Set the outputs, the standard binary outputs, the built-in ones, to anything hard-coded to system signals, and any that you want to use for general purpose, set them to IPOS output. Then do the same thing for any option cards you have. In this case, I set my whole option card input range to IPOS input, and I did the same thing to my outputs. That means my IPOS program has total control over the inputs and outputs on my expansion card. You need to tell it what kind of motor encoder you have and where it's connected. So in this case, I have a motor encoder plugged into connector X15 on my VFD encoder card. So go ahead and set that up. You need to specify how it's connected. You may have to set some of these other parameters depending on what kind of encoder you have. I'm using just the defaults here, which is fine for this kind of application. Then pick a referencing mode. We will go into referencing modes in great detail a little later. I just picked referencing mode 1 for now, which is actually what we'll use in a lot of our programs. And that's it. Once you've done that, you're all set to write and test your IPOS programs. So your VFD is ready at that point. So pause the video and go do it on your demo unit. And if necessary, go back, look at what I just outlined. Then when you're all set, come back here, unpause, and we'll see how you did. Okay? All right, let's see how you did. Let's see what you achieved. I'm going to go through and do all these steps very quickly, and you can compare it. And if you had any problems, hopefully this will show you what you did wrong. You can get it fixed. So here we go. Here's how I'm going to do it. Okay, well, we are now ready to configure our MOVIDRIVE B for IPOS programming. As you can see, I've started up MoviTools Motion Studio. I am plugged into my demo unit with a USB 11A USB adapter. I have a very standard SEW training demo unit. It's got one of the smaller MOVIDRIVE Bs. It's got a CMP50 servo motor attached to it. The servo has an AK0H encoder with an electronic nameplate. I have a control box with switches and lights, and I have a DIO11 I/O expansion card. I also have that field bus card as well, although we're not going to use that till the very end. So pretty standard. You, of course, may have a different setup. So what you need to do during your startup may vary a little bit depending on your motor and encoder, but I think this will give you the general picture. All right, first thing I have to do is scan into my system. So I'm going to just do a network scan. And there's my MOVIDRIVE B. So I'm going to pick this, and I'm going to go to the parameter tree. And first thing I'm going to do is factory reset my VFD. So I'm going to go to parameter 802, and I'm going to say delivery state. This will wipe my VFD. So of course I never do this without first thinking, should I make a backup? In this case, since this is a demo unit, of course I don't have to do that. So I've gone ahead, gone through my factory reset. There we go. I now have a clean VFD. So the first thing I have to do is a motor startup. So I'm going to right-click on my VFD, pick Startup, and do an online startup here. And pick Perform Startup. And I'm just going to go ahead and use parameter set number 1. And I'm going to execute a complete startup. And I'm going to go with a standalone motor. Now, I have an electronic nameplate, which makes my life a little easier. So you can see that it's just automatically acquired all the necessary information. I'm just going to accept that. Can't do anything here again because I have an electronic nameplate, so it's just hard-coded to what I need. And again, here it's got all the information. It's pulled out of here. Everything is fine. I've confirmed it with the motor nameplate. So we're good there. Now, here I need to do something different. I don't want speed control. I want positioning with IPOS. This allows me to have full control in my IPOS program, so I'm going to pick that. Now, normally, of course, in a real application, you'd want to tune your motor. I'm not going to do that. This is a demo unit. It's a motor with just a flywheel, so I really don't have to do much of anything to it. But of course, in a real application, you'd certainly tune it. So I'll pick that. I'm also going to just take my proposed values and accept those. I'm going to do one thing here, though. I'm going to change my pulse width modulation frequency to 16 kilohertz so I don't hear that annoying squeal when I run my motor. I'm going to accept all my tuning proposals. Again, it doesn't matter for a demo unit, but for a real thing, you certainly would set these. And I'm going to, again, just accept all my proposed values here. They're fine for a demo. But in a real application, you would certainly want to go through these and make sure you've picked appropriate values. And that's pretty much it. So now I just click Finish, and it will download the settings into my VFD. And there we go. We're all set. And I'm looking at my VFD, and it's not showing any faults, so it's ready to go. Now, what I should probably do is I should just quickly drop into manual mode and see if my motor turns at least, because it wouldn't be a great thing to continue and find I actually don't have it working. So I'm going to click Activate Manual Mode. Now my controller's inhibited, so I have to go flip the switch on my control box so that the VFD is allowed to run. As you can see, I've just removed controller inhibit, so we should be good. So I'll click the Start button and move my speed slider. And my motor's whirring away. I'll check both directions. All right. Everything looks good. I'll click Stop, deactivate manual mode, and that's it. Okay, so I've completed my basic startup. Now I have to go in and configure a number of parameters to make them suitable for IPOS. So I'm going back to my parameter tree here. And I've got a number of things to set. So I'm going to follow the same order that I showed you in the slides. So we'll go ahead and start with parameter 700 and make sure the operating mode includes the word IPOS in it. And it does. It says Servo plus IPOS, so that is good. Next, I will go to parameter 302 and look at my limits and make sure I've got my motor maximum speed set correctly, and it's set to 4,500 RPM, which for a servo motor is just great. So that's all set. Now I'm going to go to 9, 13, and 14 to look at the travel speeds. And you notice I've got them here defaulted to 1,500 RPM. That's kind of slow for a servo. I'm going to set them to 10% less than the maximum speed, so I'll set them to 4,000 RPM. It's a good round number. Remember with parameters, always remember to hit enter after you key them in. Don't just tab out of the field or the value will just default back. So I've set those. Now I go to parameter 923 and I check my lag error, and I'm just going to leave it at 5,000 increments. That is fine for a demo unit. Again, a real application, you'd want to think about that a little more carefully. I'm going to go to parameter 834 to see what the fault response to a lag error is, and it's an emergency stop with VFD fault. That is fine for this situation. I now must set up some of my IOs, so I go to 600 through 606. These are the built-in digital inputs on the VFD. And again, these really aren't crucial what I set them to, so I'm just going to set them to something that works fine for this class. I'm going to set the first one to enable and stop. I'm going to set the second to just a generic IPOS input. I'm going to set the next one to the reference cam. I'm going to set the next two to limit switches right and left if we want to do something with limit switches. And I'm going to set DI6 to a generic IPOS input. And finally, I'm going to set the last one to fault reset. So that's the settings for my built-in inputs. I'm now going to go to 620 and set the built-in outputs to a number of values. And the first one, ready, is fine. Second one, not fault, is fine. I'm going to set this one to IPOS referenced and the next one to IPOS in position. That's just kind of handy. We can see those on the lights of the control box. And the last one can just be a generic IPOS output. All right. Now, I have an I/O expansion card, and I'm very definitely going to be using it. So I need to configure it. So we'll go to 610 through 617. These are the option card inputs, and you notice they're all set to no function. So I've got to go set all of these to IPOS input, or IPOS can't access them. So this is kind of a nuisance, just to have to go through and do this 8 times, but we want those IOs, and we're going to definitely be using them. Our control box is wired up to them, so it's able to control all of these. So there we go. We must do the same thing to the option outputs. So we're going to go to 630 through 637, and we're going to set them to IPOS outputs. And that way we can turn the lights on, which are attached to these. Our control box has lights, and we can use this for some feedback. If you forget to do this, your program will try to turn these on and nothing will happen. All right, so there we go. We've configured those. We need to check one thing here on the encoder on 941 to make sure it's showing that the encoder's connected appropriately, and it is. It's connected to connector X15, and I have that all set, so that's good. And then the very last thing I need to do is to go to parameter 903 and pick a reference travel type. I will pick number 1, left end of reference cam. And that is it. I have now got my VFD configured for IPOS programming, and my motor works, so I'm good to go. And that is it. All right, that is the end of session 1. We're now set up to do IPOS programming. Our VFD is ready, and you've gone through kind of the overview. So that is the end of this video. See you in session 2.